mostly going to be a lot of reviewing from physical sciences, and we're going to talk a little bit about some math strategies in this chapter. So a lot of this chapter's homework is actual word problems in math. It's just trying to get you used to doing some of those strategies and thinking that way for when we actually start applying it for our chemistry things that we're going to learn about. So particularly in this chapter, we're looking at defining matter, looking at measurements. We're going to talk about scientific notation a little bit and significant figures and why they're important, and problem solving. And that's really what this chapter is. So really, I could skip it, but I don't want to because I really want to give you a good basis for the rest of the class. We started talking a little bit about properties, so in composition. And a big thing that we'll see throughout this class and any other chemistry class you're going to take is what the molecule is made up of is really going to dictate how that molecule behaves in a standpoint of safety and a standpoint of reactivity. So we really want to consider that. So if matter is composed, if its composition doesn't change from one sample to another, it's going to be a pure substance. We often will think of tap water as not a pure substance, that's a mixture. When we discuss water in chemistry and science, we're discussing DI water, which is an actual sample of water, of H2O, of as pure of water as we can get. So when we have a mixture of different compounds, that's going to be called a mixture. But if we have only one compound or one element, that's a pure substance, and a pure substance has properties that are not going to change from one sample to another. And that's really important. We can even kind of think about that with tap water in general, even though it is kind of a mixture, but because almost all tap water is a mixture of about the same thing, its boiling point is always going to be 100 degrees Celsius. But we do know that pure water is going to have a boiling point of 100 degrees Celsius, and that's a really important concept. So we have those properties. So this is just pure substances are made up of one type of particle, whereas mixture is made up of multiple particles. All samples show the same intensive properties, and those we're going to talk about in a little bit more detail. But for mixtures, the intensive properties can be different because a mixture, you might have a different amount of one substance in the mixture and another. So that's going to affect how that mixture behaves because one sample might not be exactly the same as the other. And pure substances are going to be pure samples of either elements or compounds. Whereas mixtures can be either a heterogeneous mixture or a homogeneous mixture, and we'll look at that in more detail. We can have a mixture of multiple elements or multiple compounds, but pure substances can only be either elements or compounds if we have only that in a sample. So we can look at elements. Elements cannot be further broken down. When we talk about that in chemistry, we usually discuss decomposed. They're not going to be decomposed. They're the basic building blocks of matter, and they're composed of a single type of atom. They may be, when we're talking about elements, combined with other atoms to form molecules. Whereas compounds can be decomposed to the elements, so they're made up of multiple elements or multiple amounts of the same element. And all molecules of a compound are identical, so if I have a pure sample of water, all molecules of water look the same. So that's what we mean by identical. As long as I'm talking about a pure substance again. Oftentimes we'll talk about water in this class, but remember, there's a difference between tap water and water. When we're talking about water in science, we're usually talking about a pure sample of water. Unless if I specify it being tap water or ionized water that has ions dissolved in it. And that'll be important conversations as we go throughout this class. So typically we'll talk about our elements, the things on the periodic table being in the elemental form are not. And that's going to be also an important distinction. For example, we have elemental chlorine versus the way that we usually see chlorine, which is as a chloride ion, which is ionically bonding with usually a counterion, sodium, potassium, things like that. So we'll see that a lot. Most natural pure substances are compounds. There are a couple of elements that exist as elements, but even when we talk about elemental chlorine, we're talking about Cl2 and not just Cl. Elemental hydrogen, we're talking about H2 gas. And we will talk about and discuss later on in further chapters why hydrogen exists as H2 gas in the natural substance and not as hydrogen as we talk about it on the periodic table. And we'll get into that in more detail. As far as mixtures, there's a couple of the two main ways that we talk about mixtures are either as heterogeneous mixtures or homogeneous mixtures. They're both mixtures, but in a heterogeneous mixture, we have a complete separation between our two things that are mixing. So they're made of multiple substances whose presence can likely be seen. If you think about sand in water, that's a mixture, but the sand, we can shake it, it'll disperse, but then we can definitely tell the difference between the water and the sand. If we look at something like a salad dressing of not a creamy Italian, but usually a normal Italian, which is a mixture of water and oil, you can see the difference between the water and the oil because they form two layers because they don't interact with each other. So that would be a heterogeneous mixture. A homogeneous mixture is a mixture where we can't tell the difference. For example, if you take your vodka and you look at your vodka, it looks like vodka. But you're likely not having a pure sample of alcohol. It's going to be alcohol that's mixed with water. And you can't tell the difference between the alcohol, the ethanol in the vodka, and the water. And it's not going to be 200 proof because you shouldn't drink 200 proof ethanol because you would get really sick. So it's not going to be a pure substance, and that's a homogeneous mixture. You can't tell the difference. Most things we're thinking about are homogeneous mixtures. For example, blood. You look at blood, it doesn't look like a bunch of different things, so you can't separate components out, but it's made up of blood cells, it's made up of hemoglobin, it's made up of a bunch of different things in the blood. So that would be an example of a homogeneous mixture. So as far as our heterogeneous mixtures, different samples can have a different composition and properties. I might have a sample of wet sand that has a lot more water. That's going to be a lot different from a sample of wet sand that has just a little bit of water. And you'll be able to see that difference. It'll have different properties. It'll have a different weight, things like that. With our homogeneous, if I take tea and I take a sample of my tea, I'm going to have the same amount of all of the molecules that are dissolved in tea because it's completely homogeneous and spread throughout. So that's our difference with our properties. So if I make a sample of tea, everything's the same concentration, and I take a little bit out of it, it's going to have the same properties as that original sample of tea, unless if I dilute it with more water. So that's our difference between our heterogeneous and homogeneous. So speaking of some of those properties, we also need to talk about, and again, a lot of this chapter is a summary of a bunch of concepts that are going to be basic concepts that we're going to go into more detail throughout and use throughout. So this particular chapter is kind of going to be a bit of information thrown at you, but not a lot of very detailed information, some general knowledge that you should probably already know just from physical sciences, even if you haven't had a good chemistry class from high school. But I want to go through them anyway, because when I'm talking about them later, I want you to know what I'm talking about. So when we're looking at our changes, different things can happen. We already talked about our different states of matter. We can have solid, liquid, and gas. And when we're looking at a compound where we're altering the appearance or the state, but we're not actually changing the chemical composition. And this is whether we're talking about a pure substance or a mixture. So if we're talking about tea again, we're not changing the actual composition, we're not diluting it. If we take that tea and then we freeze it, it's just going to be a physical change, but we're not changing the chemical composition of the tea. So when we talk about physical changes, what we're typically talking about is changing state, that changes the appearance, that changes what we're looking at. So that's our physical properties. And we'll discuss physical properties a lot in this class. Like I said, I am passing around a roll. Hopefully it gets to the back But if you don't get to sign it, just after class sign it. And if you really don't get to sign it again, it's just for my records. It's not like I'm really going to be taking up points or anything if you don't have it signed. I just want an idea of who's here and everything like that. So just make sure you try to get it signed. If we think about, for example, again, water. Our water can go from liquid to gas. That's not changing the structure. It's still H2O. It's just changing how our different H2O molecules interact with each other. So that changes the state of it. So those physical properties are really important. What the molecule or what the mixture or what the element is or composed of is going to affect these physical properties. But for a pure sample of water, the boiling point's not going to change. Now, if we're altering the chemical composition, if we're actually changing something about the chemicals, that's where we're going to look at chemical changes. And that's what we're going to be focusing on in a huge amount in this particular class, because of course this is chemistry. So what we're going to be looking at is chemical reactions, actually changing the chemical makeup of our substances. So if we have a chemical change, the atoms that are present rearrange into new molecules, though, again, remember, we're not making or forming new atoms. They're there at the beginning or the end. Now, there will be times when we form gases, and gases can evaporate. But if we have a closed system, then whatever we start with is what we're going to have at the end of the reaction. But we are changing what's actually the chemical makeup. So we might take H2O and we might remove a hydrogen to make OH minus and H plus. So that would be a chemical reaction that's actually changing the molecules. One example, and this is just one example, if we have iron in the presence of oxygen, O2 in the air, we can have an oxidation reaction that will form iron oxide, which is rust, and then we can actually see the rust form. That's a chemical change. We're actually changing the compound. We have iron, and then it reacts with O2 in the air. So that's going to form iron oxide. So that's an actual chemical change. Now, if we take a pure sample of iron and we melt it, that's just a physical change. That's not an actual chemical change. So we have chemical changes that can occur because we force them to, as we do in a chemical lab, but some chemical changes will occur because we're surrounded by chemicals all the time. We have oxygen in the air. We have water in the air. Water can react with a lot of things. So we have reactions that can occur without us making them occur, and that happens all the time. Of course, we're going to exploit reactions we can force to occur in lab. That's what a chemist would do. So our physical properties are characteristic, and I said this a couple of slides ago, of what we have. And they are directly observable. We can see, we can measure the melting point of a compound by using an apparatus and see what temperature it melts at. And in organic chemistry, we'll also often use these melting points to determine if our compound is pure and if it's in agreement with what's known melting points. Because again, a pure sample of a compound has these physical properties that don't change. So if I have a pure sample and I know the melting point, and I have an unknown sample, I can compare them. There are some limitations. There are multiple compounds that have similar melting points, so you have to have an idea of what you're starting with. But we can use those properties and observe them to understand what we're looking at. And our chemical properties are characteristic of our molecules as well. And how our matter changes is going to be a result in the contact with other matter, influence of energy. We'll be looking at all these concepts in art. I just said organic. We'll look at that in organic also. But in this class, we'll be looking at it from the standpoint of general chemistry in both this class and when you take 106. So we will be looking at these properties. And we'll see, again, these characteristics describe the behavior of our matter. So again, our chlorine ion behaves a lot differently than our elemental chlorine gas. And we'll see those differences in chemical reactions. And so some common physical changes that aren't actually changing our molecule, we already talked about boiling. Condensing is just going from a gas to a liquid. So on a hot day, you see the condensation on the outside of a glass. Try to get it, pass it back, pass it forward. Melting and freezing, subliming, you should know that term. There's not a lot of molecules that we'll often look at, or a lot of substances where we'll look at subliming, but it's basically where we go from a solid to a gas and we don't go in the liquid phase. Can anyone think of something that does that you've come into contact with? Dry ice. So CO2 will sublime straight from dry ice to solid into the gas, and you won't form a liquid in between. So there's a couple of compounds that do that. We can actually make caffeine do that under pressure, and we sometimes do that in organic labs. So when you take organic lab, you might do that. But it's a little bit less common because not as many molecules actually do that without going in the liquid phase. But we do see that. Other things that you might not consider, it is still just a physical change, typically, to dissolve something. So if we take sugar and we dissolve it in water, we still have sugar, we still have water. We're not actually getting a chemical reaction. It's just dissolving. And what happens, and we're going to look at that in more detail later on, especially when we talk about solutions in later chapters, are our water molecules are going to break up our crystal structure and surround our sugar molecules, but our sugar molecules don't change. They're still sugar. We can boil off the water and we still have sugar. So that's still going to be a physical change. We're not actually chemically modifying the sugar or the water. We're just making a homogeneous mixture by mixing them together. So as far as common chemical changes, anything that's releasing energy, burning, when you're doing your nice little crawfish boil, when you burn your propane, that's a chemical reaction. We'll be looking at a lot of chemical reactions. Not all of them, some chemical reactions take in energy. We call those endothermic. So if you get one of those chemical ice packs from Walgreens, you bust open the chemicals inside, they mix, they cause an endothermic reaction. They are actually pulling energy from the surroundings. And we're going to look at thermodynamics in a lot of detail in this class. And it makes the cold pack feel cold. So that's still a chemical reaction. I'm sorry? Did you have a question? This is an exothermic reaction. The cold packs are an endothermic reaction. They pull energy in. And we're going to look at that in more detail when we talk about thermodynamics in a later chapter. We're going to look at that in a lot of detail. Well, when we're talking about a chemical process, we're changing something about the chemical composition. We won't always see a huge difference in the change in energy. And again, in this particular chapter, we're really just doing an overview. And we'll be looking at, in a lot of detail, some thermodynamics of what happens when we have a chemical reaction. So we'll look at more examples of those kind of things. But it's a chemical change as long as we are changing the chemical makeup. We are actually breaking or forming new chemical bonds. So if we just mix water with sand, we're not changing H2O. But if we actually break a bond between our water, oxygen, and our hydrogen molecules, that's a chemical reaction. So the physical change doesn't actually change our element or our compound at all. But the state can change. Okay. Now, as far as changes, we may see either a gaining or releasing of energy, even in both physical and chemical changes. Of course, we know to boil water, we have to heat that water up. We are going to look into more details about what happens in boiling, what we are actually disrupting when we're boiling something later on. Because again, this particular chapter is more of a review of terms, but we're going to go in more detail about what's happening in a lot of these things. So Energy is the capacity or the ability for work to occur. And work is just the action of force applied across a distance. In chemistry, we'll often be talking about thermodynamics, and we'll be devoting a whole chapter on thermodynamics, the exchange of heat, which not a lot of heat in this classroom. It's freezing in here. We'll be looking at that in a lot of detail. But we're also going to be looking at energy in that particular chapter in a lot more detail than what I'm showing you here. But energy is our capacity to do work. You can think about it as you have a box. It's going to take you some amount of energy to move that box. So we're going to be applying some sort of force to a box to move it. Electrostatic force is the push or pull on objects that have an electrical charge. And because in this particular class, we'll look a little bit about covalent bonds, but a lot of the reactions we'll be talking about will be ionic reactions. And even in organic chemistry, when we're talking about covalent bonds, we'll often be going through intermediates that have charge. And when we really dissect electrons and protons, those parts of our atoms have charge. A lot of what we'll be talking about is electrostatic force. And a lot of what's going to drive our chemical reactions is going to be the attraction between positive charge and negative charge. So the electrostatic force is going to be fairly important as we go on and discuss in more details. So all matter possesses some sort of energy. And it's classified as kinetic or potential energy. Again, this is a review from physical sciences, something that you've probably learned since 9th grade. And we'll get into more details when it's appropriate. But our energy it can only be converted from one form to another. So when our matter, whether we're talking about molecules or atoms, undergoes a chemical or physical change, the amount of energy in the matter can change as well. It can accept energy from the outside. It can release energy. And we'll get into those terms a lot more in our thermodynamic chapter. But the thing I really want to touch upon is kinetic energy. So kinetic energy is our energy of motion. And our atoms, our molecules, even though we can't see it, they're always moving somewhat. In the solid state, we don't have as much molecular motion, more what we're considered vibrations. But if nothing's going on, you can't feel the molecules in, let's say this is wood, but it's probably a polymer. You can't feel them moving. But they are, but they're moving on a really, really small scale. But those motions are really important. When we go into a gas phase, we have a lot more molecular motion. So we're going to have a difference in energy there. When we talk about thermal energy and I talk about thermodynamics, what I'm typically talking about is heat and the transfer of heat. So we'll be looking at that in a lot of detail as well. And you can think about thermal as a transfer of heat. Now, potential energy is the energy that's stored in matter. And we're going to be looking at the potential energy to understand things like molecules that are stable versus molecules that are unstable. A molecule that's unstable is typically going to have higher potential energy, and it's going to be what we call more reactive. Because most molecules in nature want to exist in the most stable amount that it can. So when we see our elements being in a certain form, elemental chlorine as Cl2, elemental hydrogen as H2, it's because H2 is more stable than hydrogen as we draw it on the periodic table, which is why in nature we have it as hydrogen. So we're going to look at that concept of stability and potential energy a lot in this class. We're going to take that on to 106. We're going to specifically look at that in details in organic chemistry, because that's really what we're studying when we're looking at organic chemistry, is the stability of molecules, potential energy. So we're going to really be focusing on potential energy and the chemical potential. If it's a more unstable compound, it's going to be more reactive. That's why I can take elemental sodium metal, which is sodium. You don't usually see sodium metal in your everyday life. You have sodium ions. sodium chloride in salt, sodium ions dissolved in water, you're always seeing sodium. When you talk about sodium as far as nutrition that you're eating, it's the sodium ion. But sodium metal is the actual metallic form of sodium. And if I take sodium metal and I open a big chunk of sodium metal in the air, I wouldn't, because it would be very dangerous, because it's so reactive, it's so high in potential energy, that it would catch on fire as soon as it comes into contact with a small amount of water. Which is why sodium metal is sold in mineral oil, to protect it from water, because it's so reactive. And we'll be looking at why sodium metal is so reactive. We will answer that question later on in the section in the semester on why sodium metal is so reactive. And I don't actually have any sodium metal, but I do have potassium metal, so I'll probably bring some in, put some in some water, and show you how it catches on fire. It's quite fun. But I don't recommend putting a large amount because it can actually blow up. So you have to be very careful with it. And we'll talk about things like potential energy and how that dictates chemical reactions. And these kinds of things we'll be studying. Yes?
So going from sodium ions to sodium metal, is that a chemical change?
So we won't go from a sodium ion to sodium metal because we're going to learn that based on thermodynamics, that's something really hard to do because sodium metal is less stable. But from going from sodium metal to the sodium ion, that is a chemical reaction. Because the sodium metal is going to react with water by giving up its electron and changing its chemical composition to form an Na+. So that will be a chemical reaction. And we're going to look at that in more detail when we're talking about ions and how our atoms react. So we will look at that in more detail, but that would be a chemical reaction. Sodium metal, elemental sodium, and sodium ion are completely different things. They're made up of the same element, but they're different compounds. They're, even though technically not a compound, they're different substances. Just like going from chlorine gas, Cl2, to the chlorine ion, Cl minus, is going to be a chemical reaction. But like I said, in most cases, you're going to come in contact with sodium chloride because the sodium ion and chloride ions are much more stable, have lower potential energy, so therefore they're not very reactive. And we are going to look at that in more detail. Again, this chapter is more of, here's some general background information you need to know before we really delve into these things in a lot more detail. And we'll look at concepts of energy and matter when we get to thermodynamics in more details. So this isn't going to be the only time you see some of these definitions. And I'm going to show you these definitions and then we're never going to see them again. Showing you definitions that we're going to use throughout the class to get more information from it. So if we're looking at this 10 kilogram thing and it's hanging off the side of the building, it's going to want to fall. That's going to be our high potential energy. As it's falling, there's kinetic energy, and then its lowest potential energy is when it's going to be flat on the ground. It's no longer wanting to fall. And we're going to be considering and visualizing that as chemicals, as molecules, as compounds, as elements. And that's often how we'll draw them. If something's higher in potential energy, we'll show it higher on the diagram. If something's more stable and lower in potential energy, we'll show it lower. But once this thing falls on the ground, it can stay on the ground until someone moves it. But when it's up here, it's going to eventually fall. So that's what we'll be looking at with chemical reactions. How stable is it in the potential energy where it is? How much more stable is it in this other potential energy? So comparing sodium metal, those are kinds of things we'll be looking at. Sodium metal is up here, sodium ion is down here. So we'll be, and I'll try to bring in analogies. I know you can't see chemicals sometimes, most of the time, so I'll try to bring in analogies when I can. And always raise your hand if you want to ask more detailed questions. But this particular chapter, we won't get into as many details. So talking about energy, energy can't be created or destroyed, but it can be transferred. It can be transferred from potential energy to kinetic energy. Heat can be taken from the surroundings and put into a system, meaning if I'm going to put a glass of water in a room and nothing changes about the room, it's a glass of water. If I put a glass of water in the sun, the glass of water might start evaporating, but that's because we have the surroundings, the sun, giving off heat energy to our glass of water. So that's our law of conservation of energy. Our total amount of energy remains the same, but energy can be converted to different forms. And again, in thermodynamics, we're actually going to look at the math of this. And we're always going to be, in all the equations we're going to learn. We're going to learn a lot of equations, especially in thermodynamics. But it's all based on this fact when we're talking about energy, that energy isn't created or destroyed. It can be transferred. But the total energy is always going to be the same of our system plus our surroundings. Another term I want to be really specific about. What do you think spontaneous means? Let's not have this slide up. Random. What else? When you think about spontaneous, what are you thinking?
Very quick.
Very quick. A lot of people think, oh, spontaneous, so I'm just going to have the spontaneous idea and I'm going to go to Biloxi right now. I'm leaving. Bye, y'all. That's not what we talk about when we talk about spontaneous in science. When we're talking about spontaneous, when we're describing chemistry specifically, but anyway, science, but when we're describing chemistry, it's a term you're going to hear. Spontaneous has nothing to do with a process that's fast. Spontaneous just means that a natural occurrence we're going to have in a spontaneous process, our products are going to be in more concentration. Our reactants are going to be more concentration than our products at equilibrium. So spontaneous just means our product formation is favored. It doesn't mean that our product formation is going to happen fast. It just means that our formation of our product is favored. The example of sodium metal reacting with water to form sodium ion is a fast process and a spontaneous process. But there are spontaneous processes that form a more stable product than our starting material that are very, very slow. For example, diamond into coal. That could take thousands, if not millions of years under a large amount of pressure for diamond to be converted to coal. But coal is more stable than diamond. So on a potential energy scale, diamond's up here, coal's up here. And coal is more stable, so our product is more stable than our reactant, but it's not a fast process. So in this class, when you hear spontaneous, all you should think is the potential energy of our products is lower than the potential energy of our reactants. That tells us nothing about how fast the reaction is going to occur. We're going to discuss what causes reactions to be more fast or slower, but it doesn't have anything to do with the term spontaneous. And I want you guys to realize this before we start talking about thermodynamics, before we get into chemical processes more. Because when we talk about spontaneous now, you want to think it doesn't have anything to do with time. It only has to do with our product potential energy being lower than our reactant potential energy. So our products being favored. It could be fast, but it might not be fast. And again, in thermodynamics, we're going to graph this out. We're going to visualize this. But I want you to start training yourself in this class and any science class when you think about spontaneous. That's all we're thinking about and no longer thinking about time, which I know is how most people think about spontaneous that are not studying science. So when we're talking about some releases of energy, a good chemical process, and this is a chemical process we can discuss, is a combustion engine. Now, combustion is a chemical process, so what we're doing is burning. And in the combustion engine, we have gasoline. Gasoline molecules are roughly unstable. And then we have a combustion engine that converts our gasoline, releases energy, propelling our car forward, and then releasing our molecules in exhaust, which is our breakdown of our gasoline, and we're going to look at the combustion reaction to CO2 and H2O. And it's not just clean, CO2 and H2O, because gas doesn't burn clean. Some things do. If it did burn clean, you're just forming CO2 and H2O, but then your exhaust would not be kind of muddy looking. So there's other small carbon-containing things that are also released in combustion, because gasoline is a mixture. It's not just a pure substance. But we're going to look at combustion a lot more. But combustion releases energy. Energy propels the car forward. When you are boiling your crawfish, you are burning propane. Again, that's another combustion that releases heat energy. That boils your water, allows you to boil your crawfish. You light a lighter, that's butane, and again, you're lighting something. It's combustion that releases energy in the form of a flame. So we're going to be looking at those concepts. So now that we talked about some general knowledge that we're going to be applying, now we're going to talk a little bit about units. It's going to be really important. So we're going to start off with looking at units and then talk a little bit about converting units and just some concepts there before we actually start working with math. If you can understand this now, the rest of the class is going to be so much easier. Because converting units is, we do that all the time. If you want to do something in the medical industry, you need to know how to convert units because usually you won't prescribe a drug for each person. Say you take 30 milligrams, you're going to prescribe a drug as this patient gets 30 milligrams per kilogram body weight. So I can prescribe 30 milligrams per kilogram body weight, and then someone has to convert that to the exact amount of the drug that person needs based on their body weight. So conversions are going to be really important. It's important in the lab because you don't want to mix compounds in not the right amount and cause an accident or just not cause the reaction you want or not a high enough yield. In the medical setting, you definitely don't want to give someone the wrong amount of drug because you couldn't convert units. And even though, yes, technically you can have some software to do it, still, again, when you're giving drugs to someone, you want to be able to convert that. And don't think that just because clearly, if you're in this class, you're probably not a nursing major because that's a separate chemistry class. So if you're interested in the medical industry, most people are probably pre-med. Though you do not need to be pre-med to get into medical school. Just a side note. Always think about your backup plan because not everyone in this room who's pre-med is going to get into medical school your first try at least. And I always get called, oh my God, Dr. Cortez is so mean for saying that, but it's true. Not everyone's going to get into medical school. It took my husband 3 years before he got in. And then he had to get a master's in between and bring up his MCAT score, and he taught at the Princeton Review for MCAT classes for a year before he got into med school. So you always want a backup plan, and no one cares about pre-med. But you can still take all the classes. If anyone wants to discuss career stuff, I'm always available for that as well. I never want to squash anyone's dreams, but you should be realistic and have a backup plan. Anyway, my husband, who is a psychiatrist, often has to convert units to converting drugs when he's giving them to his patients. Because you don't want to give the wrong amount of drugs to a psychiatric patient. You don't want to give the wrong amount of drug to a chemo patient. You want to be clear with that. And doctors do that. It's not just the nurses that do that. It's not just the techs that do that. Everyone has to do conversions. It seems like just a simple or a really low-level thing, but if you can work with your numbers, work with your standard units, work with conversions, it's very important. And it's not just converting units for drugs in the medical setting. You're going to give a test to your patient. You're going to get this list of levels of whatever's in their blood. And they're not all in the same units because one compound in the blood might typically exist in a very small level, so it has a smaller unit, versus something like sugar might be a bigger unit. So to compare them, you have to have an idea of what a milligram is versus a gram. You have to have an idea of what a microgram is so you can visualize when you're reading a chart, when you're reading these kinds of things, when you're in the lab. So units are going to be very, very important. And I like to spend a little bit amount of time with it now before we actually start going into the theory of chemistry where we're going to be applying it. But it's really important. It might seem like, oh, I got this answer wrong. I just had my decimal place off. Well, a patient might say, I died because you just had this decimal place off. You might blow up a lab because you just had this decimal place off. So it might seem simple, or I should have gotten full credit for this. It's just a simple math mistake. And it's not when you're giving it in the real world. So we want to talk about units. We want to think about them. And Because we live in the US, most of our standard units are not going to be what we're used to working. For example, Celsius and Kelvin. We won't be working with Fahrenheit very much, but that's what we think. Even as a scientist, and I've been a scientist after grad school, after doing my 5 years of grad school, being a scientist, doing research, I still have a hard time for me to think about temperature outside in anything but Fahrenheit. And I was in a lab, and when you're in a graduate program, you're typically in labs with people from all over the world. And I was in a lab with a guy who was from South Africa, and I was like, oh, what temperature is it outside today when I lived in Minnesota? And he's like, 30 degrees, or no, lower than that because it was Minnesota. 10 degrees Celsius. I'm like, I don't know what that means. He's like, you're a scientist. You work in Celsius all the time. I'm like, I know what it means for my chemical reactions. I don't know what it means for me to be outside. Because we don't really think about those terms. So for us, being American, we really kind of sometimes need to think about our standard units a bit more because we don't use them as often, like kilometers instead of miles. So thinking about that and training ourselves to visualize what that is important as scientists, so we don't make simple mistakes. If I write a paper and someone reads it in Germany, they should be able to read my numbers. So we have a standard unit. Our System International is just our international systems of what units are agreed upon for measurements in science. So that's our SI units. For example, for length, we're thinking about meters. Mass, we're usually looking at kilograms, not pounds. Again, if you're giving a drug in the medical setting, you're usually looking at micrograms per kilograms, milligrams per kilogram. And when I say that, we mean microgram drug per kilogram body weight, not pounds, kilogram. So even in the medical setting, you're already converting things from pounds to kilograms. So that's our agreed upon mass. Time is seconds. Temperature is Kelvin, though in the lab we use Celsius a lot. Most thermometers don't really read Kelvin, they read Celsius or Fahrenheit. We usually use Celsius. We'll talk about conversions, of course, in temperature. Kelvin is agreed upon, though, because absolute zero is the lowest temperature, and therefore temperature is always in a positive number. Versus Celsius and Fahrenheit, you can have negative Celsius, negative Fahrenheit. So we usually use Kelvin, especially in equations, because it can't be negative. So that's really useful. So let's talk a little bit about length. That's our two-dimensional distance. We'll usually see that with a yardstick or a meter stick, a ruler, things like that to look at our length. Often needed in measurements, we can look at long distances. We can look at length from here to the moon, or very short distances between atoms. And of course, in this class, we'll be focusing on those very short distances a lot more because chemistry is the study of how molecules and atoms and elements behave. So we're usually talking about really small things when we're talking about length. But in this particular homework section, we'll be looking at big things, small things. It's just an idea to get you to start thinking about word problems the correct way and applying the math and converting units. So our SI unit is meter. That's about 3.37 inches longer than a yard. And the reason why, 1 meter is the distance traveled by light in a specific period of time. So meter is no. Conversions for meter, things like that I'll give you. You don't need to memorize them. You don't need to know how many inches and all of that. I'm not making you do that. I'm not testing you in your ability to memorize conversions. I will tell you when there's things that you need to memorize. I particularly don't really think that memorization is necessarily going to help you out in the long run for something you can easily look up. Things that we use a lot, like for instance Avogadro's number, you're going to have to memorize that, but you won't have to really because we'll use it so much that you'll learn it. But things that you could just look up easily, converting inches to something else, I'll give you those conversions if I ask for them. What I'm testing you is your ability to do the conversion if you have the conversion unit. So that's what I care about. So I won't be doing that. So some commonly used, you'll often see it in centimeters because a meter is bigger. And again, 1 inch is exactly 2.54 centimeters, but you don't have to memorize that, I'll give you that. Conversions from centimeters to meters, we'll talk more about those conversions. You will have to memorize those. But we'll talk about that in a little bit, couple of slides. So just those. Now mass is the amount of matter present in an object. Don't get this confused with weight. Mass is the amount of matter present. Weight depends on your gravitational pull of an object. You're going to have a different weight if you're here on the moon, but your mass isn't going to change. So typically we'll discuss mass in science because we want to look at that. That is independent of gravity. So our SI unit is typically kilograms, which is about 2 pounds or 3 ounces. Again, if we're doing those conversions, you won't have to memorize that. So commonly 1 kilogram is 2.2046 pounds, and 1 pound is 453.59 grams. That's just for you to get an idea of how they relate. Especially, again, we as Americans typically consider our weight in pounds. So when you're talking about giving a pharmaceutical and it's in milligrams per kilogram body weight, that really kind of gives you an idea of thinking about and visualizing that conversion. But you don't have to memorize the numbers because I'll give it to you. And then, of course, we can go kilograms to grams or milligrams if we're talking about something that doesn't weigh a lot. Like in the lab, we'll often do small scale reactions. So instead of weighing things out in grams, we'll weigh them out in milligrams. Micrograms, which isn't on here, oftentimes you'll be using a milligram or a microgram per kilogram body weight because you're not giving a huge amount of drug to a person. You're giving a very small amount of drug relative to their weight. So we can use those different sizes to understand it. But typically, we're looking at kilograms as our SI. Time is just the duration of an event, and seconds is what we're usually using. And it is 1 second is the period of time it takes for a specific number of radiation events in cesium-133. So that's kind of where seconds comes from. And again, well, you probably already have memorized how many minutes is in a second and all of those, but we'll still talk about those conversions and being able to do those conversions. Because a reaction might take seconds, it might take milliseconds, it might take minutes. So we want to be able to do those conversions, but the SI, the standard unit, is seconds. Temperature, again, we're looking at the average kinetic energy. Higher temperature, larger average kinetic energy. Heat flows always from high temperature to low temperature. So that's the way heat always flows until they reach the same temperature. So if you put ice in your water, it's not that your ice is cooling down your water, your heat in your water is actually being transferred to the ice. And then that makes your water feel colder to you because the energy was transferred. And then eventually all your ice melts and then you have room temperature water. So that's what we're looking at, and that would happen with heat. And I'm going to stop here. Oh, I didn't have any. We're going to have more iClicker questions typically, but because I'm still getting all the iClickers in and giving you some time to get some iClickers. So next class, I will definitely have iClicker questions, so make sure you have your iClickers so you can start getting your bonus points. Where's my roll? Does anyone have? Okay. If you haven't gotten to sign the roll, please come and sign it. We won't be doing this for all classes. I'll be using the iClicker.
Got quick break, so like first off, I have something we need to sign.
Yeah.